I thought I would actually give the proof of the lower bound on the Deutsch-Jozsa algorithm. So let's remember how that goes, and then I'll give the proof. And actually, well, the proof is kind of a cheat, because what it does is it takes a very powerful theorem from combinatorics and then applies it and gets the result. But none of these lower bounds is at all, if you try to prove any of these lower bounds from scratch, they're all hard. So I'll do this one, and I'll just present the hard part as a lemma. OK. So what was the Deutsch-Jozsa algorithm? Deutsch-Jozsa. Alice has x1. Well, Alice has a bit string x1. Bob has bit string x2. Either x1 equals x2 or x1 equals x2 bar. So this is x1 plus x2 is constant. Or the Hamming distance between x1 and x2 is equal to n over 2. So they differ on exactly half of their bits. And this is the case. x1 plus x2 is balanced. And now we pull an obscure combinatorics result from the combinatorics literature. It's by Frankel and Riddle. So let n be divisible by 4. I have no idea where this comes from. And ST are subsets of n-bit strings. So this is one set of n-bit strings, and T is another set of n-bit strings, such that the Hamming distance between ST is not equal to n over 2 for S in S and T in T. So suppose you have two sets of n-bit strings such that the Hamming distance between any string in this set and any string in this set is not exactly n over 2. Then the size of S times the size of T is less than or equal to 4 to the 0.96n. So you can see that this condition is exactly what is not allowed for ST. And as Berman's paper remarks, this result from combinatorics seemed custom made for proving a lower bound on classical Deutsch-Jozsa. So what is the result again? What result do we want to prove? So Alice has x1. Bob has x2. And they have a conversation, x1, x2. Alice sends some bits to Bob. Bob sends some bits to Alice. And then Alice says, either x1 equals x2 so let's either x1 equals x2 or the distance between x1 x2 equals n over 2. So we start out with two strings which are promised. They're either equal or the exact opposite or balanced. And actually, for this lower proof, we can relax it to the case they're either equal or they're the Hamming distance between them is n over 2. And Alice and Bob are going to have to decide after some length of their conversation. And I want to claim this should be less than n over 100 bits. So if they send less than n over 100 bits back and forth, they cannot do this. So really, this, when Alice sends information to Bob, it's not only the bits she sends that conveys information, but also the last, it's also how many bits she sends could convey information. And what we want to do is we want to say that the total information conveyed is at most n over 100 bits. So we should encode this conversation in some way that that makes the total information conveyed less than 100 bits. And you can do this something like 0, 0. 0 means 0, 0 means 0, 1, 1 means 1, 0, 1 means end of message. It's your, or what is it, over and out. So assume that we've done some kind of encoding so that the total number of bits sent is at most n over 100. Now, there is some record of this conversation, which I need to find a new variable name for. So let's call R the conversation. So that gives us both Alice's messages and Bob's messages. So there are at most 2 to the R equals 2 to the 1 to the n over 100 conversations. Now, let's look at Alice's strings and Bob's strings. So 1, 2, 3 through 2 to the n, and 1, 2, 3 through 2 to the n. So if Alice has, actually I probably should say 0, and 2 to the n minus 1. So if Alice has 0 and Bob has 0, then, and they use whatever protocol they're using, they will get some conversation and R1. And if they both have R0, if they both have 1, then they should have R1. If they both have 2, they should have R2, all the way down to R2 to the n minus 1. And of course, this matrix has a lot of other entries in it. But let's just worry about the ones along the diagonal. There are 2 to the n over 100 conversations total. Are 2 to the n over 100 possible conversations total. And there are 2 to the n entries along this diagonal. So there exists some R that appears 2 to the n over 100 times. No, 2 to the, I'm doing this wrong. There are 2 to the n conversations total, or 2 to the n entries along this diagonal. Each of them is represented by 1 conversation, and there are 2 to the n over 100 possible conversations. So there are 1 conversation that appears 2 to the 0.99 n times. Good? Okay, so let's just mark which things it appears and which things it appears in here. And we'll call this set S, and we'll call this set S as well, I guess.